So, good morning everyone, and welcome to session number 1 on heating and cooling. I'll be the chair for the session. I'm Neil Burnside from the University of Strathclyde. And this morning we're going to have Miriam, Ahmed, Musa, and then Neha. And Neha's going to join us online, okay? So 10-minute presentations followed by about 5 minutes of questions. And we'll try and stick to that if we can, please, since we're already running a bit behind schedule. So without any further ado, I'd like to welcome up Miriam Isidik, thank you, from University of Glasgow, who will give her presentation on defrosting operation of a flexible heat pump cycle.
Good morning, everyone. I'm Miriam, and I'll present you our work on defrosting operation of a flexible air source heat pump cycle from our group at the University of Glasgow. So to give you a bit of background on heat pump, heat pumps are seen as the way to decarbonize the heating sector, like the main way to do it. And so far, 180 million of heat pumps have been installed in the world for heating application. And according to the International Energy Agency, we'll need to reach 600 million of heat pumps in the world to reach net zero in 2030. We'll need to get heat pumps to reach 20% of the heating demand in the world. And so far, they are only reaching 10%. So more work needs to be done to make them efficient and more widespread in the world. And the current situation led us to an unprecedented will to switch to heat pump with everything that's been happening in Russia and Ukraine. So far, 60% of the global heating is still provided by fossil fuel. So to give you, if you don't, I guess you know what a heat pump is, but to give it very simply, it's a thermodynamic device that works with electric power. So it doesn't emit CO2 by itself. And the refrigerant will go through, you have a refrigerant in the cycle, and we go through 4 steps. So for transformation, so you got the compression from state 1 to 2. On the bottom of the slide, you could see the pH diagram for that. So from 1 to 2, it's a compression, so it consumes electric power. From 2 to 3, it supply it inside and it's being condensed. From 3 to 4, it is expanded. And from 4 to 1, it is getting heat from a heat source. So in the case of air source heat pump, it will be air. And because of that, air source heat pumps are very flexible because you can install them everywhere. To describe the efficiency of a heat pump, we'll use a COP, a factor that we call COP, a ratio. So it's the heating supply divided by the compressing power that's being consumed by the heat pump, and you get a number superior to 1 for that. The issue with heat pump is that if you have a big difference of temperature between the source and the supply, then the efficiency will drop because you have to consume more power. In the case of air source heat pump, we also have another issue, which is frosting, that can happen when outdoor conditions are very cold and humid, which will happen often in the winter. And the issue is that it will drop the heating capacity of the heat pump, and then it can't provide heat inside as it would used to, and it will consume more power. The issue is that that will drop also the COP, which is the efficiency, and it will slow down the widespread in the market because to sell a heat pump in the EU, you'll need to get 3.8 of scope, which is the seasonal coefficient of performance, the performance on a year. And in the winter, this performance might drop. So what we did with our group is that we tried to find a way to put heat storage inside the heat pump cycle to recover subcooling heat, which I will explain a bit later, to make it more efficient and it will help widespread the use of heat pumps because it can lead to power reduction consumption, and it will lead to a higher temperature uplift, and that can also be used to provide continuous heating when you're defrosting. So our flexible heat pump is, this is one of the layout that we are working on. Like that, it's not very, it's a bit confusing, but I'll get into it later. And basically, you go 3 modes. So the first mode is the normal heating mode. The heat pump works as a normal heat pump with a difference, is that the refrigerant, after being condensed, is subcooled in a heat storage, and it charges heat inside. This heat is being stored for later use, and it doesn't change the efficiency of the heat pump when it runs in normal mode. And then this heat that has been charged can be used to uplift the temperature of the source, because now the evaporator will not be the outdoor unit, it will be the heat storage, so that the source temperature is higher, and then you use less compressor power. So this is the second mode. It can help you reduce your using of electrical power. So for air source heat pump application, we can do that with the modification. The difference is basically that the mass flow rate after being evaporated, the refrigerant after being evaporated in the heat storage will split in half, and into not necessarily in half, but one part will go through the evaporator that's been frosted to be defrosted, and you'll still provide heat inside with the rest of the mass flow rate. And the evaporator will be defrosting at the same time, so you keep continuous heating inside. You defrost the evaporator, and you uplift the source temperature. So you have 3 perks of that, is that you have continuous heating during defrosting, you use less power, and you can uplift the temperature. Here are some results that we made on this application, on the defrosting application. So on the up left, you have the COP average. On the up right, you have the improvement compared to a normal baseline heat pump. And what we can see is that depending on the temperature of storage, you could have better or less improvement compared to a COP, to a regular heat pump, but you always have improvement. So the COP average is basically the COP that the heat pump reach on the whole charge and discharge cycle. So you take the COP on the whole cycle and on the whole charge discharge cycle, and you compare it to a COP of a heat pump, regular heat pump, and that will give you the improvement. So for our work, we found that we can reach up to 18% of improvement with that, and that this improvement will increase when the condensing temperature increases. So that's the figure on the bottom. And the optimal thermal storage will also change and increase with the condensing temperature. We did also simulation with different refrigerants to see how it will work. And we found that some refrigerants work better than others with our system. And the one that works the best are the ones that have the lowest enthalpy of vaporization, because they can recover more heat by subcooling. So this is the case for R410A, which works the best with our system, but also some refrigerants such as R1234ZE, which is a lower global warming potential refrigerant replacement for R134A. It works, it does have a better improvement than R134A with that system. And that led us to a future prospect that this system could help use the use of low global warming potential refrigerant. It will help widespread the use of air source heat pump. it will provide, it can help us reduce our electricity bill by just saving power when defrosting or without defrosting, just by recovering some heat from the internal cycle. So we did have a paper on that, not the layout I showed, but another one with more detail on how it works. So if you're interested by that, you can check it out. And thank you.
Thank you very much, Miriam. It's a fantastic talk. Do we have any questions in the room? I think. There you go, please.
Hi, Dave Lincoln from Harvard University. With that added flexibility, have you looked at applications around sort of demand response and being able to respond to signals from the grid? Because that's a problem with e-commerce. They don't really like to flex, but have you looked at that as an actual application trying to quantify the improvement?
Well, not yet, but we were just looking at theoretical performance so far. So it's just a concept. We just started to make a rig and to see how it could work individually, but it's definitely something that our group could look into in the future. But yeah, thank you.
Okay. Any more questions in the room? Have we got any online questions?
There's a question.
Oh, pardon. Here we go. On you go.
I'm just curious about whether this is an issue in Scotland when it gets cold enough for air source to come to the freeze,
Yeah.
or if it's more associated with other countries.
This is definitely an issue in Scotland because it asks for humidity, a high level of humidity, and a cold weather to make frost on the outdoor unit. So this is a Scotland problem. This is also a problem in other places, but Scotland is very humid, so yeah.
Oh, we've got a bunch of questions. Can everyone hear me okay? Yeah, okay. So, Miriam, can you elaborate on government's policy for reuse and or repurposing of existing oil and gas infrastructure in just transition? Right. Wait. Sorry, I think that may be a question for earlier. It's just come through.
I'll try my best.
Okay, so any more questions? This all seems to be energy transition questions, taking a long time to come through. Any more questions in the room?
What sort of heat store would it be integrated within the heat pump or would it separate?
It's integrated inside the heat pump. So yeah, this is what makes the flexibility, because you don't have to have an external device. It's inside, and you can use latent heat or sensible heat. So for our rig that we just started to do, we used a water tank, which is quite simple actually. So and it still worked. We can't reach 18% of improvement, but we still reach improvement. So.
Hi, Colin Smith, University of Edinburgh. I was just wondering from the picture, I know you said it was kind of theoretical at this point,
Mm.
would the actual technology look much different? Would it be bigger? Would it kind of have more parts? I'm just thinking from a kind of social perspective, one of the things that I found in some research is that people do care about the aesthetics in some cases and don't want some big equipment kind of
Mhm.
attached to the side of the house. So yeah, would it look kind of as heat pumps do at the minute, air source heat pumps, or would it be quite different kind of aesthetically?
Well, the rig that we made is a regular size heat pump. So as I was saying, we managed to get some improvement with that. Of course, it's up to improvement, but it shouldn't change the size of the heat pump, because if we can just use a water tank and make it efficient, then it's not much. It's just a regular heat pump with a water tank. So normally it shouldn't change, but for bigger application, obviously it would be a bigger heat pump.
Any more questions? So, very quick for myself. So, in terms of thinking of that, could you couple a heat pump then to pre-existing water tanks already within homes and dwellings? or would it need to be a completely new system?
Well, if we can make it, if we can change, we just have to add the storage between the condenser and the expansion valve. So essentially, it shouldn't change much, but it might change in the configuration of the heat pump and how it works. So in real application, I would say it doesn't need a lot of changing. So, yeah.
Okay, great. Well, fantastic. Thank you very much, Mariam.
Thank you.
So next up, oh sorry, my bad. So next up we have Ahmed El Tayeb, who will give a presentation on thermal conductivity enhancement of fluids.
Good morning. My name is Ahmed El Tayeb from University of West Scotland. First thing I would like to say that my research is focusing on heat transfer fluids, especially nanofluids. But to start this research, we had to make a device for thermal conductivity measurement. How to? Okay. The nanofluids are simply nanoparticles made by different ways and mixed in base fluid, which could be water, could be oil, could be any fluid. The nanoparticles thermal conductivity. The nanoparticle thermal conductivity is higher than the nanofluids thermal conductivity is higher than water, and we can see here that the conductivity could increase 30% when we add Ag2Al, and also 140% for Ag2Al, and for aluminium copper is 120%, which could increase the efficiency of heat transfer, especially in buildings or industrial cooling and heating. So it was important to choose the method for thermal conductivity measurement. The most used method for thermal conductivity measurement is the transient hot wire method. Most of the researchers, they use this method for determining the thermal conductivity of fluids, gases, and even solids. The transient hot wire is a very thin wire in microns, maybe between 25 to 100 micron, hanged inside the fluid. There is a lot of sensors that has been made before. As you see in the slides, there's different ways to put the sensor hanged in the gases or liquids. The basis of this, the theory of the transient hot wire is when we heat the wire using electrical current, joule heating, the wire will start to heat. But if we have a fluid around the wire, this will help to cool the wire. The rise in the temperature difference will determine the thermal conductivity of the wire. The signal should be taken. We need linearity in the signal. So the best way is to use Wheatstone bridge. Wheatstone bridge will ensure the linearity between the change in the resistance of the wire, which will change due to the heating of the wire, the temperature of the wire. After that, this signal is very weak. You know, we are talking about microvolts. So it should be amplified, and then to analog to digital converter to get the signal, to get a file for the signal. The analog to digital converter is simply an oscilloscope. This is the circuit, as you see, the Wheatstone bridge, and the analog to digital converter. After that, the analog to digital converter is connected to the computer for processing this signal. The signal needs a lot of equations after that to get the thermal conductivity. This is the device that we've made. I think you can see the circuit inside the box. I made the box like that because I had a lot of instruments around us in the laboratory. So these instruments causes a noise for the signal. So I made something like a Faraday cage around the circuit. The photo of the wire is the photo here. The wire, can you see the wire? Can you see? Okay, it's very thin. Yeah, it's 75 micron. 75 micron, yeah. It was difficult to solder it, really. It was very difficult. This is the circuit. The results from the wire, I made a MATLAB simulation for the circuit output. The simulation, the red curve is the simulation, which represents no fluid around the wire. There is no change in thermal conductivity. There is nothing absorbed the heat from the wire. So as you see, the curve is, the shape of the curve is ideal. But the figure up is for methanol. You can see the change in the curve, the curvature. I take this information after plugging the information in the equations and do some matrices, some mathematics. I get straight line. The slope of the straight line, then plugged in equation to get the thermal conductivity. As you see here, I have a lot of noise due to the equipment that I had, a lot of noise, electronic noise. Yeah. So after that, I try to avoid this noise. And I use the MATLAB also application. I made a MATLAB application to get the calculation done immediately without doing it using Excel as previous in this the other side. Excel was very difficult because using a lot of informations and sheets like that could lead to some confusion in the program. But MATLAB was much better. And I get the signal with the straight line like that is very nice, very clean. This is the thermal conductivity of alcohol, which is fairly good, 0.2, as reported in other literatures. The validation of the device, for the validation of the device, I measured the thermal conductivity of different liquids, glycerol, 2-propanol, methanol, water, and I get these results, which is reported in other literature and is good, is not bad. The accuracy is not extremely, I don't know, but it's not bad. The future work will be the formulation of new heat transfer fluids and the implementation of these heat transfer fluids for domestic and industrial heating. I would like to think about implementing, instead of using oscilloscope, implementing an FPGA for signal processing and get the whole device in one place with the sensor. Thank you very much.
Thank you very much, Ahmed.
Yeah, thank you.
Any questions in the room? Yeah.
It's about, I can have differences, 0.01 or 0.03 maximum. Is 5%? 5%, yeah. 0.5%, yeah, sorry.
Can you buy the, presumably you can buy these pieces of equipment off the shelf? What's the accuracy?
It's too expensive. Yeah. I asked the university, but they don't have funds for that. It's too expensive, yeah.
Follow-up question really is, obviously you're talking about measuring conductivity. Your project primarily is about the application of nanofluids,
Yes.
improving thermal conductivity. Why would you want to look at that? Why is that important?
The nanofluids? The thermal conductivity of okay. If we use propylene glycol for heat transfer, the conductivity of propylene glycol is 0.25, which is less than water. Water is much more efficient than propylene glycol, which the thermal conductivity is 0.6. So if we can use something more conductive than water, this will increase the efficiency of heat transfer. So we will lose less energy in...
So how will it benefit me as a homeowner?
Huh?
If I own a house, I have heating
Yeah, okay, you will pay less.
How will it help me?
You will pay less. You will pay less in the energy bill.
Okay.
Maybe around 15% estimated by my professor. Yeah, thank you.
Anyone else got any questions? Can I ask a speculative question then?
Sure.
Do you have any feelings on what is more conductive than water?
Metal.
Metal.
If we can put the liquid metal, it will be very nice, but we cannot.
Are you able to?
This is the idea. If you pack the water with metal, this will increase the thermal conductivity of water, but nanoparticles.
Okay, would it even be with certain degrees of different dissolved states of types of metal? So some metals are very readily dissolved in water, for example, so basically to be dosing the water.
Yeah, 1 second, 1 second. This question is very critical. Nanoparticles are not ions. You have the real metal hanged in water.
Right, okay.
Okay, it's a real metal, it's metal. It's metal, very tiny particles that is hanged in water due to Brownian motion.
Okay.
So it's not dissolved.
Okay. So you want insoluble metals?
Insoluble, yes.
Right, Brian?
Thank you.
Anyone else?
I suppose following on from that, is the increase in efficiency worth the price of these?
Yeah, 15% is very good. I have calculated it is very good. 15% saving in the energy bill is very good, especially for factories. Yeah. They use nanofluids in nuclear reactors. They use it. Yeah.
Okay, any other questions?
Can you use the electric machine cooling?
Yeah, sure. Yeah. They can use it for cooling and heating.
Okay, Brian, I think that'll do us. Thank you very much.
Thank you. Thank you very much.
Can I just point out a really important question that Professor Harrison posed there, and that all researchers need to think about is, and so what? Why are you doing your research? How does it affect Professor Harrison and his energy bill or whatever? Okay, this is really important for the general public to know, so that you just don't get involved in the technology and lots of equations.
Yeah, I'm sure it's getting drummed into. I'm sure that's getting drummed into a lot of PhDs just now because it's annual review time. So I'm sure you're all thinking about that as well as doing your presentations here. Okay, so now could we please have up Musa Zerai from University of Edinburgh, and Musa is going to give us a presentation on intelligent, sustainable heat transformation.
Okay, can you hear me well? Hi. Hi, good morning, everyone. My name is Musa Zari. I'm a current PhD student at the University of Edinburgh. Today, I'm presenting my project, which is an intelligent sustainable heat transformation, supervised by Professor Aristides Kiprakis and Dr. Thomas Morstan. So we are developing a virtual heat plants to decarbonize the heating sector. I will start my presentation by giving you an overview, introduction about the decarbonization of the heating sector, and then moving into the aims and objectives of our research, followed by the methodology, and then I'll give you just an overview of what's the current work we are doing and what are we planning to do. And finally, I will conclude what's the some of the results that we've already generated and what's the expected outcome of this project. So starting with a quick overview of the heating sector. So heating demand accounts for almost half of the UK total energy consumptions. As can be seen in the figure 1, the emissions from the heat are the single biggest contributor to the UK emissions, and the decarbonization success we've seen in the power sector must now be replicated into the heating, so we can meet our climate commitment. So for this will require a fundamental shift away from fossil fuel into a low carbon heat technologies. So here we are proposing the concept of a virtual heat plants, VHPs, and which is a collection of an individual heating system are collectively considered to be a single virtual provider of heat, creating a smart thermal grid management system. For this, we will use, oops, it's not moving. Okay. So for this, this will be based on a self-learning algorithm, including dispatching, forecasting, and planning models. And the concept of VHPs will help to create a strategic, localized management of distributed heating resources, and the heating service at a building level will be provided by a multiple or single heating system, for example, electric or gas, and we will also have a scenario for hydrogen boilers. So this can be grouped and managed at a regional level by aggregator to meet the total demand by combining the heating technology within different buildings. And the proposed concept of VHPs is based on the aggregation of a building storage capacity combined with the demand side management. So the main objectives of this work is to demonstrate the operation of VHPs and investigate their use as a provider of flexibility with an ultimate goal to decarbonize the heating sector. So to achieve these objectives, we are developing a smart VHPs grid management optimization strategy that uses a self-learning algorithm to perform the management action controls for forecasting and planning. And then we will also optimize the smart thermal generation from a multi-vector generations. And finally, we will optimize the building demand by a direct control through a heating set point temperature. So for that, we first need to get the thermal demand profiles for a different building archetypes and a different occupancy profiles. So here we use a HISIM, which is it's a household infrastructure and a building simulator. This is an open source package for simulating an analysis of a household scenarios and a building system using a modeling components such as a heat pump, gas boilers, and hydrogen boilers. So using this, we already achieved our first objectives, which is creating a library of a different building archetypes with a different, so we can model their thermal behavior considering a different heating systems. So models of these will have to be integrated into the overall demand model and interact with the occupancy as well as the weather. And for information about the occupancy, presence, and activities, we are using a load profile generator tools. It's a software where we can generate occupancy profiles based on like what we use. For example, like we can choose how many people are living in the property and if they are working from what time to what time, like for example 9 to 5, and when do they need the heating, and then we feed that into the Python package, the HiSim, to actually generate a different demand profile. So, and then we also developed a machine learning algorithm model to predict the gas consumption for space heating, including in building. And we will set like a visual threshold for the forecast model to predict the higher usage within the peak hours. So after that, we will use an open source database, OpenStreetMap, to visualize the data, and then by doing so, it will allow us to understand how flexibility is become available at a single household level, and then aggregated into streets, neighborhood, and different areas. So this is, I mean, after that, we will be able to plot an individual time series and then aggregate it once again at street, neighborhood level, and towns. And then we would be able to understand how flexibility becomes available at a single household level, while people like live their life in and out of the property and as a function of their activities and behavior. And then again, we will aggregate it at a neighborhood, street, neighborhood, and a town level. So here, just to conclude, so once the aggregated flexibility is done, here is the main contribution. This will help us to assess its value as a function of time, location, and weather, and then we will be able to suggest a management strategy and improvement. The main idea of the VHPs is about using the flexibility of buildings that equipped with the multiple sources of heating so we can create a virtual flexibility and improve the balance and the heating balance of a building. And this is like just an example to make things clear. So if one building has a gas boiler as the heat source, and other building has gas boiler as a heat source and a heat pump. So to balance both networks, we could give a signal to the building that has the heat pump to use more of the heat pump, while we have more renewables using like tools, API tools to give us the live generation of renewables. I forgot the name. I think it's the carbon intensity. Yes, and yeah, that's where we create the virtual flexibility, and this will allow us to trade heat as a service to virtually combine the load of energy system, and that provides heat ultimately for everyone at the lowest cost and the most environmentally friendly way. And that's the end of my presentation. Thanks for your attention.
Thank you very much.
No problem.
Do you have any questions?
Just can you expand a little on your sort of data sources? You mentioned your library of building types.
Yes.
And also your need to have some activity data of some households. So can you just maybe expand a little on where that data comes from and how you can make it statistically meaningful and robust?
Yeah, so HiSim is an open source package. So we use it to generate the demand profiles, the heating demand profiles. This is an open source, so we can take it and just actually just improve it the way we want it to. And we also found another software which called the load profile generator. So it can also create the it can create the demand profiles for us and for the buildings, but it's actually, the main purpose of that tool is to generate occupancy profiles. So it could specify like everything in the, like it's too much details you can specify in that tool. You can say how many people lives in there. You can say if you want, like if they're working 1 day from home and 4 days from the office. You can say, you can include weekends activities, travel plans, Christmas plans, and that will generate like their presence and activities. So we use these files and feed it into the open source package. That creates a different demand profile, so we can use it.
Just very quickly, what temporal resolution will you need for those profiles to account for diversity so that this is a meaningful virtual power plant kind of calculation?
Sorry, say that again, please.
The temporal resolution on the profiles, what do you actually need? How high resolution do those profiles actually need?
That's like not, like it's not been looked at yet, and this will be looked at in the next step with a different.
I think you're asking what time step is.
Oh yeah, what time step? Sorry. So we got like a 15-minute time steps.
Okay.
Yeah. Sorry, I got the question. Yeah.
Question over here.
Yes.
You had gas and electricity grids in your picture there,
Yes.
but not district heating networks, and yet I would argue that district heating is a critical part of any virtual heat
Yes.
plant.
Yes. Yeah, so that's for sure. So, but we're like our main focus of this project is to include a gas boiler and the heat pump and try to create, like, to provide flexibility for both networks. And the point we always argue is about heat networks is it's very expensive and it's very early to create a scenarios or study for it, like based on this project at least. But it could be for future researchers to develop or to pick up where we stopped. Yes.
One of the principles of the electrical virtual power plants is that you share heat in and out of the system. So you share electricity in and out of the system.
Yes.
Here you're not really doing that, are you?
So here we're using a different management strategy. So we give a signal to the houses, for example, is to like, so we use the building itself as a heating storage. So instead of firing up the boiler at 6 a.m. At 6 p.m. during the peak time, we give a signal to switch or like to move the load like earlier time at 3. But there is no actual like heat would be.
So essentially it's a sort of form of kind of demand-side management
Yes.
shared across people for the benefit of the grid rather than trading, if you like, trading.
Yes.
Event.
Yeah.
Okay.
Yeah.
Thank you.
Thank you for the presentation. I saw on your slide you talked about you're looking at the thermal behavior of the buildings.
Yes.
So what sort of, have you had any results from that, the thermal performance?
Yes, so we use a data source called topical, which provides a building archetype for 12 countries in Europe, pre-1990 till 2010, and that's what we're working with a different type of building, detached, semi-detached, terraced, and a building apartments, and at different ages. So we've got some results for different type of buildings, but there are like lots on the table and lots of building types and lots of occupancy profiles. So we need to be careful of what we're choosing because this is a 3 years project.
Okay, brilliant. Thank you for all the questions and thank you very much for the presentation.
No problem.
Fantastic. Now, hopefully, we've got Neha online. So the next presentation will be Neha Mehta from the University of Birmingham, and she'll be presenting on decarbonisation of heat using heat pumps, a life cycle assessment study.
Okay. Thanks, Andy. Hello, everyone. I'm Neha from University of Birmingham. and based in energy policy group. And I'm actually delighted to be here and listen all the talks on heat pumps and cooling and different materials for them. My study is based more on life cycle impacts and how environmental impacts can be measured, and what are the systems uh, system-wide approaches that are linked with heat pumps. Could you please go to next slide? Yeah, thank you. So why heat pumps? I think a lot of it is already covered in the talks before me, and we have. Uh, I think one thing we need to realize is that if we want to meet the net zero targets in the UK, we should be looking at the decarbonization of heat as well. A lot of decarbonization so far has happened in electricity, but not in heating sector. And which leads me to the second point, which is that heating, if we include the industrial processes, today accounts for about 37% of the UK total greenhouse gas emissions, and about 40% of the energy is consumed in heating. So this is where the heat pumps can play a role. And I think I want to also focus on the point that it's not just heat pumps, it could be also hydrogen boilers or biogas or more efficient insulation at the housing or the building sector. But I would be focusing on heat pumps predominantly today. Next slide, please. Now, when we talk about heat pumps, and we also know or have studied so much that heat pumps can lead to a reduction in greenhouse gas emissions, but what happens to the other environmental categories? What happens to, let's say, acidification or eutrophication, and how much have we studied them in detail? So for this, we use life cycle assessment, and life cycle assessment is an analytical tool that sits at the interface of science, engineering, and policy. For every decision that we take, there are always consequences, good consequences, bad consequences, and also they can be synchronous, sometimes asynchronous, and which is why it is important that if we are suggesting a wider change to to heating sector, we should be knowing what environmental impacts are we going to deal with. So the 4 stages of life cycle assessment includes goal and scope mapping, which is what system boundaries are we studying? Are we going to study cradle to grave or cradle to gate, or are we studying consequential approaches? What will happen if end of life management is not included in the studies, or what if it is included? So the first stage of the life cycle assessment itself includes system boundary definition, where we should define how much of the impacts we should be studying, and for what processes. And the second stage is functional unit. So will we be measuring environmental impacts for, let's say, 1 kilowatt hour of thermal energy produced, or thermal energy produced for a year, or thermal energy produced for the whole operation life of the system, and then find the environmental impacts associated with it. The second stage of life cycle assessment is inventory analysis, where we should quantify all the energy, materials, and emissions involved. And this is the phase where it needs a lot of input from businesses, installers, even the households who have already installed. How are they facing the efficiency changes from whatever was at the beginning of the installation to now after 10 years? And it involves a lot of input from also businesses, in the sense that we would need to know what are the materials used in the heat pumps, where were they sourced from. The third stage is impact assessment, which is where we select the variety of impact categories, and for example, ammonia emissions, SO2 emissions, sulfide emissions, all the emissions, water footprinting, carbon footprinting, amount of energy used in totality or amount of renewable energy used, and last is interpretation and reporting. What were the uncertainties involved? Were there, do we need to make comparison of different products, and what if the heat pumps themselves are made with different refrigerants or different materials, solid state materials. And next slide please. So a generalized system boundary of life cycle assessment of heat pumps will involve raw materials, energy, electricity, transportation, and the stages would include manufacturing. It will include piping, casing, heat transfer fluids, installation, um, all the preparation of the building for installation of the heat pumps, operation, what is the source of electricity, end of life, whether we are recovering plastics, are there recycled refrigerants, metal and oil, and the last one is what are the waste produced in the system, what are the emissions to land, emissions to air or water. Next slide please. So we started reviewing the uh, studies published in the last 5 years to understand what different system boundaries or what different functional units were used for understanding a life cycle impact assessment of heat pumps. And we used such terms as life cycle and heat pump. The reason why we didn't put life cycle sustainability assessment or life cycle assessment in itself is because we didn't want to exclude life cycle cost estimations. Even though we are focusing on life cycle sustainability assessment, it's important that we also come across life cycle cost estimations. And so far from these 375 articles in the which are published in the last 5 years, we have analyzed 100 of those studies, and 25 of them have been studied in detail. And the first major result that we got is that in all those 25 studies, goal and scope, like the functional unit itself is different, or the boundary conditions are different, and even the region is different, like the regional analysis. For example, some studies can be from Italy, Turkey, Lebanon, anywhere, which means that no one study was actually similar to the other. And that means that if ever we have to make decisions on the life cycle environmental impacts of heat pumps, we will have to know what region are we talking about, what electricity mix are we talking about, what materials we are talking about. Next slide, please. So these are characteristics of the reviewed studies, and as I mentioned earlier, we had functional unit different. Some of the studies focused on how much heating was required for particular household or for a particular building in a region or particular type of building, or heating of water, or and the processes that were analyzed were different in the sense some processes were for air source heat pumps, some were for ground source heat pumps, and some were like combining air and ground. So different sorts of processes, and the product use was different as well. Like in some certain systems there was use of cooling rather than heating, um, or even some of the studies just compared refrigerants and the differences in LCA tools, LCA methods. So one of the things that often gets overlooked is it's not just a system boundary or the inventory. Even the difference in LCA methods can lead to differences in results, and or the differences in the final environmental impacts reported, which means that every impact recorded should also have a method attached to it, and some of the studies didn't even mention LCA method. And the last one is what databases were used, but they primarily based on stakeholder interviews or manufacturers, or they used more general databases like EcoInvent. could you please go to next slide? Yes, so this is just continuation of all the reviewed studies, and what we have identified is that a lot of research is going on both heating but also in the cooling side, and also on refrigerant leaking and differences in refrigerants. And it is important because we would not like a certain product to have um, unintended consequences. For example, if we focus too much on GHG emissions, we might miss what is happening to other environmental impacts. Could you please go to next slide? Next. So, and the last part is of these characteristics of the reviewed studies is that um, a lot of studies focused on operation lifetime. So I think this is a very important part. Whenever we are designing products, are we designing them, for example, even within heat pumps, we came across studies which were mentioning their operation lifetime as 15 years, and some mentioned as 20 years, and some were 30 years. So we need to be careful that the heat pumps that we are producing, designing, and installing should have operation lifetime which can be longer, but also which does not, which is easy to repair. Next, please. And this, I think, I find it interesting because all the studies had different boundary conditions involved in that, involved in the analysis. Some had transportation involved, some didn't have. Though one of the thing with transportation is normally in any energy-based production, the most of the impacts are incurred during operation rather than transportation itself, which might be one of the reason why some studies didn't account for transportation. And another thing is end of life management. It's really difficult to understand the whole life cycle impacts of any product if we don't look at end of life management. So some of the studies, like I think majority of the studies looked at end of life management, but not all of them looked at it. Next, please. And I think this is also to show that even among all those 25 studies, which were like out of 100, which means I have still to go for another probably 50, 100 studies for the final analysis, there was difference in inter-operational transportation or installation even used or not. Some studies didn't account for any environmental impacts incurred during installation. Next, please. And I think I want to say what is the way forward of this review that we have been undertaking on life cycle assessment, and what are we actually going to do after understanding what different boundary conditions were studies. The first and foremost is we should try to bring all the studies to one functional unit. Right now, all the studies are in different functional units, so we can't really compare from one study to another. But it has to be noted that even if we bring from one functional unit to another, it won't be like one answer. The answer for environmental impact would be more of a range, because the studies differ in their system boundaries and the studies differ in the region reported. The second thing is, can we identify what will be the unintended consequences due to focus on heat pumps? And if there are, then how we will be mitigating those? One of the thing is that there will be more load or more use of electricity than natural gas for boilers, or in fuel poverty areas where even the oil is used right now. We will have to switch from the oil to heat pumps, and those heat pumps will need electricity. So there will be an increase in the electricity load. And another one is how those impact of heat pumps can work with between different sectors, because I think one of the question that mentioned earlier was, which was actually good, that how are we going to think about reuse or refurbishing of boilers or gas-based infrastructure, because it is not like suddenly the shift will happen now from gas-based infrastructure to heat pumps. We will have to probably make incremental changes, and we will have to also work what works best at what points. So can we have temporal impacts involved in the at a UK scale, to understand what are the environmental impacts of heat pumps, or even at the regional scale, can it be just West Midlands, or how interconnection of those factors, such as policies, funding, going to influence the renewable energy systems which are already in place. And the last one is, if we have to go for novel heat pumps or conventional heat pumps, then what recommendations can we make to support production and deployment of heat pumps on a scale? And one of the biggest is, how many households do we already have who have heat pumps installed, and what are their efficiency experiences, what experiences they have had um, in heat pump deployment, and what can we learn from these? And thank you.